Okay, let's dive right into this. Welcome to the Explainer. Today, we're taking a seriously high-energy, absolutely fascinating journey through the world of current electricity. We are going to break down everything from the incredibly chaotic life of a single electron all the way up to mapping out massive, multi-loop electrical circuits. So, if you're looking for a direct, clear understanding without any of the unnecessary fluff, you're in exactly the right place. Let's get started.
Here's our micro to macro roadmap for today. First, we'll hit the microscopic mechanics of current. Second, Ohm's law and resistance. Third, EMF and internal resistance. And finally, mastering Kirchhoff's laws. All right, Section 1, Microscopic Mechanics of Current.
To really grasp how electricity works, we have to step right into the chaotic interior of a conductor. Picture the inside of a standard copper wire that isn't even plugged into a battery. The electrons inside aren't just sitting there. They are zipping around wildly at unbelievable speeds. We're talking on the order of 10 to the power of 5 meters per second. But this is just random thermal motion. Because they're flying frantically in every possible direction, the net flow is zero. It produces absolutely no current. However, the magic happens when we apply a battery. Suddenly, we get drift motion. Now the electrons are still bouncing around like crazy, but they collectively start to slide or drift in one unified direction. And the craziest part, it happens at an incredibly slow pace, about 10 to the power of -4 meters per second. It's actually this incredibly slow, deliberate drift motion that produces our non-zero net current.
Now, you might be wondering, why is that drift so painfully slow? Well, because it is a spectacularly bumpy ride in there. As electrons get pulled by the electric field, they are constantly crashing into atoms. This brings us to a concept called relaxation time, which is denoted by the Greek letter tau. Relaxation time is literally just the average rest period an electron gets between those successive, violent collisions. Then we have mobility, denoted by mu. Mobility measures exactly what it sounds like, how agile or mobile an electron is. Essentially, it's how much drift velocity is generated per unit of electric field. So, if an electron can navigate that atomic obstacle course efficiently, we say it has high mobility.
And this brilliantly illustrates how the macroscopic stuff we measure every day relies entirely on these invisible microscopic realities. The total current I is completely dictated by N, which is the number density of electrons, E, the charge of an electron, A, the cross-sectional area of the wire, and Vd, that tiny drift velocity we just talked about. If you divide that total current by the area, you get current density, J. It's like a giant puzzle, and it's all connected perfectly. Moving right along to Section 2, Ohm's law and resistance.
Zooming back out to the macroscopic level, we generally know that resistance blocks current, right? But here's the kicker. Temperature changes everything, and it depends heavily on the specific material. For your standard conductors, like a copper wire, the temperature coefficient, which we call alpha, is positive. Heating up a conductor gives its atoms more kinetic energy. They vibrate more, collisions increase, that relaxation time drops, and therefore, resistance goes up. Makes sense, right? But wait, look at semiconductors. Their alpha is actually negative. By nature, they have very few free charge carriers. When you heat up a semiconductor, that thermal energy literally frees up more electrons to participate in conduction. So in a weird twist, heating a semiconductor actually makes its resistance drop.
Now, what's really interesting to consider is that we spend so much time in physics talking about how materials stop current, resistance and resistivity, but if we flip the perspective for a second, what is the exact opposite of resistance? If resistance is how well a material blocks flow, how do we measure its eagerness to let current through? The answer is conductance and conductivity. Conductance, denoted by G, is simply 1 divided by resistance. And conductivity, sigma, is 1 divided by resistivity. But check out the units. There's a brilliant, totally humorous wordplay here that makes this impossible to forget. The standard unit of resistance is the ohm. Well, if you spell ohm backwards, you literally get MO. The analogy from the source material is great. If you detach yourself from ohm, which historically represents the divine or God in some Eastern philosophies, you get stuck in MO, which sounds like the word for worldly attachment or illusion. So you leave ohm, you enter MO. It's such a clever, playful way to remember that these concepts are exact mathematical inverses of each other.
All right, Section 3, EMF and internal resistance. We've spent a lot of time on the wire itself, but what about the actual pump pushing the current? We constantly hear the term EMF, or electromotive force. So the absolute crucial point you need to take away here is, it's not actually a physical force at all. It's a bit of a historical misnomer. Think of it more as the naked voltage. EMF is the absolute maximum theoretical voltage a battery could provide if it were, perfectly ideal. But as we know, batteries aren't perfect. Inside every battery is a chemical soup, an electrolyte, and pushing charge through that soup causes collisions. This creates internal resistance, which we denote with a lowercase r. Because of this internal resistance, the battery effectively eats up a little bit of its own voltage before it even has a chance to reach your circuit.
This brings us to a super practical realization. When a battery is discharging, meaning it's powering your phone or your flashlight, the actual voltage you get out of it, the terminal potential difference, V, is equal to the total EMF minus the voltage lost internally, that IR part. You're getting less than the maximum. But think about what happens when you plug that battery into the wall to charge it. You are literally forcing current backwards into the battery. To pull that off and overcome both the battery's EMF and its internal resistance, the charging voltage, V, has to be equal to the EMF plus IR. You have to push harder than the battery's own natural limits just to fill it back up.
And that brings us to our final stop, Section 4, Mastering Kirchhoff's Laws. As we scale up from simple single-battery circuits, things can look pretty messy, but the tools to solve them aren't just scary math equations, they're just basic universal truths applied to wires. We really just rely on two rules: Kirchhoff's current law, KCL, and Kirchhoff's voltage law, KVL. It is totally vital to anchor these in fundamental reality. KCL, the junction rule, is literally just the conservation of charge in action, and KVL, the loop rule, is just the conservation of energy. If you just keep those two core conservation laws in your head, the math suddenly makes intuitive sense. Let's start with KCL. It dictates that at any junction or node in a circuit, the total incoming current must perfectly equal the total outgoing current. Why? Well, because charge is conserved. As the source playfully points out, there's no magical drain or trapdoor hidden inside the wire where electrical charges just fall in and vanish forever. Whatever flows in absolutely must flow out. Period. So, if 5 amps enter a split in the wire, the branches might take 2 amps and 3 amps, but they are always going to perfectly sum back to 5. Now let's see how this builds into KVL, the voltage law. KVL states that the net voltage around any closed loop is 0. But tracing a loop can honestly get super confusing with all the plus and minus signs floating around. So here is a basically foolproof traversing method. First, always try to traverse the loop in the exact same direction as the assumed current. Second, if you pass through a battery from its negative terminal to its positive terminal, that is a step up. You are gaining energy, so you write it down as a positive voltage. Third, whenever you pass through a resistor in the direction of the current, energy is being consumed. That is a drop, so you always write it with a minus sign. Step up is plus, drop is minus. Just keep it that simple and you won't get lost. So imagine a really complex circuit. Let's say it has 2 loops, one powered by an 80-volt source, another by a 40-volt source, and they share a central wire. By methodically walking those loops, adding 80 volts when stepping up the battery, subtracting I times R for every single resistor we cross, we can easily generate 2 clean, simultaneous algebraic equations. From there, it's just basic high school algebra to find the exact currents. And hey, even if your final current calculation comes out as a negative number, don't panic. Seriously, it just means the physical current is flowing in the opposite direction from what you initially guessed when you drew your arrows. The math still holds perfectly.
We've scaled all the way from a single tiny drifting electron to mapping out multi-loop systems. So to really test your mastery, there's a final, somewhat daunting circuit presented in the source material. It's a 3-loop bridge circuit involving a 10-volt battery and a whole web of 5-ohm resistors. Your challenge is to use literally everything we've just covered. Identify the junctions for KCL, pick your 3 loops, step up over the batteries, drop over the resistors, and write out those 3 KVL equations. Can you solve it? I highly challenge you to grab a piece of paper right now and find out. Thanks so much for joining.